What if I told you there's a place in the cosmos where not one, not two, but 6 suns could light up the sky at once? Imagine standing on a world where the horizon is crowded with glowing orbs, each casting its own tangled web of shadows, a celestial dance so rare, so bizarre, it defies everything we think we know about how stars behave. These are sextuple star systems, cosmic anomalies where gravity weaves 6 stars into an intricate ballet, and the rules of astrophysics seem to rewrite themselves. For centuries, we've gazed up at binary stars pairs locked in mutual orbits thinking they were the pinnacle of stellar complexity. But nature, as it turns out, loves to upend our expectations. Out there in the deep black, hidden in the glare of more ordinary systems, astronomers have stumbled upon these sextuple oddities. They're like cosmic Russian nesting dolls, stars orbiting stars which orbit yet more stars, all bound together in a gravitational puzzle that shouldn't exist. And yet they do. The mere fact that these systems hold themselves together without tearing apart is a mystery that challenges our understanding of the universe itself. But the real magic lies in the secrets these systems are slowly surrendering. Strange gaps in their orbits, unexplained flares, even hints of planets somehow surviving the chaos. Every new discovery peels back another layer of the enigma. Why are these systems so rare? How do they form in the first place? And what can their extreme environments teach us about the limits of star formation? That's the journey we're embarking on today, a deep dive into the weirdest, most baffling sextuple star systems ever found, and the mind-bending truths they reveal about the cosmos. Buckle up, this is going to be a wild ride. Among the countless stars in our galaxy, one system stood out as the first of its kind, a cosmic curiosity that shattered our expectations. Meet TYC 7037-89-1, a sextuple star system so perfectly arranged it looks almost designed. Nestled in the constellation Eridanus, roughly 1900 light-years away, this stellar ensemble isn't just a random clump of stars. It's a meticulously organized hierarchy, like a finely tuned clockwork where 3 binary pairs orbit each other in an elaborate gravitational dance. When astronomers first spotted it, the data seemed too bizarre to be real. How could 6 stars ranging from scorching giants to smaller, cooler siblings coexist without tearing each other apart? The answer lies in their structure. Picture this: the innermost pair whirl around each other in a dizzying 1.5 Earth-day orbit, so close they're practically touching. Around them spins a second binary duo, completing their dance every 8 years, and encircling them, a third pair, lazily looping once every 2,000 years. It's a celestial matryoshka doll, each layer moving in harmonious isolation, yet bound by gravity's invisible threads. What makes this system truly mind-bending is how it challenges our models of star formation. Conventional wisdom says such complex systems should collapse under their own chaos. Yet here they are, stable against all odds. Even more baffling, the stars' ages match perfectly, suggesting they were born together in the same stellar nursery, a cosmic family that stayed intact for billions of years. But the real showstopper came when researchers noticed something peculiar: eclipses. As the inner binaries cross paths, their light dims in predictable patterns, offering a rare window into their orbits. These flickers aren't just pretty, they're clues. By decoding them, scientists are unraveling how such intricate systems evolve and whether planets could ever survive in their turbulent realm. TYC 7037-89-1 isn't just a curiosity. It's a blueprint rewriting the rules of how stars can live and thrive together. But if you thought TYC 7037-89-1 was strange, wait until you meet Castor, the 6-star powerhouse of Gemini that's been dazzling astronomers since ancient times. At first glance, it looks like a single bright point in the night sky. but hidden within its glow is a gravitational circus where 6 stars whirl around each other in a dizzying display of celestial choreography. Castor's secret: it's actually 3 binary pairs locked in an intricate cosmic waltz. The primary duo, Castor A and B, orbit each other every 450 years, each one itself a tight binary with stars circling every 9 days. Then there's Castor C, the runt of the litter, another pair of red dwarfs zipping around each other in less than a single Earth day. Together, these 6 stars form a hierarchical sextuple system so complex it makes our solar system look like child's play. What's truly baffling is how these stars defy expectations. Conventional models suggest such a crowded system should be unstable, flinging stars into the void over time. Yet Castor has kept its act together for millions of years. The key might lie in its layered orbits like a set of spinning tops. Each pair moves in its own isolated rhythm, barely noticing the others. But even that doesn't fully explain how such a chaotic arrangement persists without tearing itself apart. Then there's the mystery of their ages. While most sextuple systems are born together, Castor's stars tell a different story. The A and B pairs seem older, while the C duo appears startlingly young, as if they were adopted into this stellar family long after it formed. Did a passing star cluster drop them off? Or is there some unseen force sculpting these orbits into stability? Every new observation peels back another layer of the puzzle. And here's the kicker: Castor isn't just a cosmic oddity, it's a time capsule. By studying its gravitational quirks, astronomers are uncovering clues about how star clusters evolve, how multiple systems form, and even how planets might survive in such a turbulent environment. If a place this chaotic can host stars for eons, what else might be hiding in the glare of seemingly ordinary stars? The universe, it seems, has a flair for the dramatic. While Castor and TYC 7037-89-1 represent rare stability, some sextuple systems are born into utter chaos, and HD 98800 is the poster child for gravitational anarchy. This young stellar family, barely 10 million years old, is like watching a cosmic demolition derby in slow motion. Unlike the orderly layers of other systems, HD 98800's 6 stars are locked in a relentless tussle. Their orbits so unstable they fling each other around like marbles in a spinning blender. At the heart of this pandemonium are 2 triple systems, each a tight-knit group of 3 stars, circling each other in a precarious dance. The gravitational shoving matches between them are so violent they've warped what should have been serene dust disks, the birthplaces of planets, into twisted, fragmented rings. Imagine trying to build a sandcastle in the middle of a hurricane. That's the futile reality for any potential planets here. The dust and gas that normally clump together to form worlds are instead whipped into frenzied spirals, shredded by competing stellar tides before they can even settle. What makes this system truly bizarre is how it mirrors a celestial pinball machine. Stars slingshot past one another, their close encounters altering orbits in unpredictable ways. One year, a star might be drifting lazily at the system's edge. The next, a gravitational nudge sends it careening inward, disrupting everything in its path. This isn't just random chaos, it's a laboratory for studying how extreme environments sculpt star systems in their infancy. Yet amid the turmoil, there's a tantalizing mystery. Faint infrared glows hint at stubborn pockets of dust that refuse to be scattered. Could fragments of planetary material somehow survive here? If so, they'd be unlike anything we've seen. Worlds forged in a furnace of gravitational fury, where a single year might see a sun rise in the east and set in the north. HD 98800 doesn't just challenge our ideas of stability. It forces us to rethink how planets might emerge in the universe's most hostile corners. Deep in the heart of the Scorpius constellation lies a stellar horror story. New Scorpii, a sextuple system where stars don't just coexist, they feed. This isn't a peaceful dance of gravity. It's a cosmic battleground where so-called vampire stars drain the life from their siblings, triggering violent outbursts that defy everything we know about how stars age. At the center of this drama are two pairs of binary stars locked in a deadly embrace. The larger, hotter stars, blue giants burning fiercely, are slowly being cannibalized by their smaller, hungrier companions. These vampire stars don't just orbit, they press so close their gravity strips away layers of gas, siphoning material like thieves in the night. The stolen plasma spirals into the vampire's grasp, superheating until it erupts in unpredictable flares that make the entire system flicker like a dying light bulb. But here's where it gets even stranger. New Scorpii's vampirism isn't just a curiosity, it's rewriting the rules of stellar evolution. Normally, stars age predictably, burning fuel at a steady pace until they fade. But in this system, the stolen gas rejuvenates the vampires, making them appear younger and hotter than they should be, while their victims wither prematurely. It's as if these stars are cheating time, altering their fates through cosmic theft, and the chaos doesn't stop there. The stolen material doesn't always settle quietly. Sometimes it piles up until it detonates in sudden, luminous bursts, mini supernova that can outshine the entire system for days. These eruptions are so extreme, they've forced astronomers to reconsider how binary stars interact. Could similar vampire dynamics be hidden in other crowded systems? And what happens when the victims run out of material to steal? New Scorpii doesn't just show us stellar violence, it's a preview of the chaotic, messy ways stars might evolve when gravity turns them into predators. Yet amid the carnage, there's a silver lining. By studying these vampiric tantrums, scientists are piecing together how stars exchange mass in dense environments, a process that could explain bizarre stellar hybrids scattered across the galaxy. New Scorpii isn't just a freak show, it's a clue to one of the universe's darkest, most violent survival strategies. In the constellation Cassiopeia, where most stars shine with quiet elegance, Cassiopeia erupts like a spectral beacon, a sextuple system bathed in an otherworldly ultraviolet glow. This isn't the gentle light of ordinary stars. It's a haunting radiance born from violence, where stellar winds scream outward at millions of kilometers per hour, colliding in shockwaves so intense they blaze with the energy of a cosmic forge. The result, a lighthouse effect visible across the galaxy, pulsing with eerie regularity as the stars whirl through their orbits. At the heart of this phenomenon are two massive, hot stars locked in a tight embrace, their surfaces boiling with such ferocity they fling off torrents of charged particles. These winds, faster and denser than anything our sun produces, crash into the outflows from the system's four other stars, creating a shimmering web of plasma. The collisions heat the gas until it fluoresces in ultraviolet, painting the surrounding space with a ghostly halo. From a distance, the entire system flickers like a candle trapped in a hurricane, its light fluctuating as the stars' positions shift. What makes our Cassiopeia truly uncanny is how predictable its rhythm is. Every 25.4 days, the primary stars align just so, funneling their colliding winds into a narrow beam. For a brief window, the ultraviolet glow intensifies, flashing across the cosmos like a signal. A pulse so precise, astronomers initially mistook it for evidence of alien megastructures. But the reality is even stranger. Nature, unaided, has crafted its own lighthouse, a celestial strobe light powered by pure astrophysical chaos. Yet the implications run deeper than just a pretty light show. These violent winds are sculpting the system's future. As they blast outward, they carry away stellar mass at a staggering rate, like sand slipping through an hourglass. Over time, this relentless erosion could alter the stars' fates, hastening their collapse into supernova or even black holes. Cassiopeia isn't just a spectacle, it's a time lapse of stellar evolution, showing us how the most massive stars tear themselves apart in their prime. And there's another twist. The ultraviolet glow might be hiding secrets. Some theorists suggest the winds are so powerful, They could be carving cavities in the interstellar medium bubbles where new stars might one day form. Others wonder if the system's Eerie light could illuminate distant planets passing through its glow, acting as a backlight to reveal atmospheres we'd otherwise never see. Cassiope doesn't just defy expectations, it offers a new lens through which to explore the universe's darkest corners. One thing's certain: when a star system turns itself into a lighthouse, the universe is sending us a message, written in ultraviolet, etched by chaos and waiting to be decoded. Beta Monocerotes isn't just another twinkle in the night sky, it's a stellar powder keg waiting to detonate. At first glance, this system appears to host 3 bright stars, but peer closer, and the truth reveals something far more dramatic. 2 of those points of light aren't single stars at all, they're supergiants, each one a cosmic titan teetering on the edge of self-destruction, bound together in a gravitational embrace that could end in one of the most spectacular light shows the galaxy has ever seen. These twin behemoths, separated by just a few hundred astronomical units, are monsters by any measure, so massive they make our sun look like a speck of dust. Their surfaces burn at temperatures hotter than industrial furnaces, and their cores churn with elements forged under pressures so extreme they defy earthly physics. But what really sets them apart is their fate. Both stars are ticking time bombs, their nuclear fuel dwindling by the second. When they finally exhaust their energy, they won't fade quietly, they'll explode as supernova, briefly outshining entire galaxies. Here's where the real nightmare scenario unfolds. If one supergiant detonates first, the shockwave could ripple through space with enough force to destabilize its twin. Imagine a row of dominoes, each collapse triggering the next, except these dominoes are city-sized infernos capable of sterilizing nearby star systems. Some models suggest the first explosion might even compress the surviving star's core, hurrying it toward its own demise in a chain reaction of stellar Armageddon. Yet the mysteries don't stop there. Observations show both supergiants are wrapped in thick cocoons of expelled gas, the telltale signs of stars already shedding their outer layers in preparation for death. These shimmering shrouds interact in bizarre ways, creating shock fronts where stellar winds collide at speeds approaching 10,000 kilometers per second. The turbulence is so intense, it generates X-rays detectable across interstellar space, like a distress signal written in radiation. But the most unsettling detail: Beta Monocerotes might not be alone in this dance of destruction. Computer simulations hint that in densely packed star clusters, such paired supernova could set off waves of sequential explosions, like celestial firecrackers popping one after another. If true, this system isn't just a curiosity, it's a preview of how the universe's mightiest stars might bow out en masse, their final acts rewriting entire regions of space in an instant. For now, the twin supergiants continue their slow, inevitable march toward oblivion. Whether they'll detonate in unison or staggered succession remains one of astrophysics' great unanswered questions. But one thing's certain: when they go, the cosmos will bear witness to a spectacle unlike any other, a reminder that even the grandest stellar ballets must eventually meet their explosive finale. The VV Orionis system hides a dark secret, a stellar fugitive fleeing the scene of a cosmic crime. Here, among 6 stars locked in an intricate gravitational web, one member suddenly tore free, blasting outward at speeds that defy logic. Astronomers call it a runaway star, but that label hardly captures the violence of its escape. This wasn't a graceful exit, it was a cataclysm, a gravitational slingshot so powerful, the star left behind a glowing trail of superheated gas like scorch marks across the fabric of space. What could hurl a star with such force? The leading theory points to a deadly game of celestial billiards. Picture this: in the system's chaotic core, 3 binary pairs orbit each other in unstable harmony. When one star strayed too close to the dominant pair, their combined gravity acted like a catapult, flinging it outward at hundreds of kilometers per second. The energy released in that moment would have shaken the entire system, sending shockwaves rippling through nearby dust clouds. But the real smoking gun is the aftermath, the runaway's glowing wake. As the star plowed through interstellar material, its supersonic speed compressed and heated the gas, creating a bow shock visible in ultraviolet light. This shimmering arc isn't just debris, it's a fossil record of the ejection, preserving the exact angle and velocity of the escape. By studying its curve, astronomers have reverse-engineered the event, pinpointing when the star broke free roughly 30,000 years ago. Yet mysteries linger. The runaway's trajectory suggests it didn't act alone. Some hidden force, perhaps an unseen companion star or a rogue gravitational kick, gave it an extra push. Even more puzzling, the remaining stars show no signs of the disruption such violence should cause. Their orbits remain eerily pristine, as if the system simply erased the event. This cosmic whodunit challenges our understanding of stellar dynamics. Normally, ejections leave systems unbalanced, yet VV Orionis seems unfazed. Could multiple stars have conspired to stabilize the chaos? Or does this system possess some hidden symmetry that absorbs such shocks? Each question leads deeper into the enigma of how sextuple systems survive their own internal revolutions. One thing's certain, the runaway star of VV Orionis isn't just a cautionary tale. It's a Rosetta Stone for decoding the extreme physics of multi-star systems. Its scar across the cosmos whispers secrets about the fragile truce between gravity and motion, and what happens when that truce shatters. Hidden in the depths of the constellation Lupus lies a cosmic jewelry box, HD 144548. A sextuple system where stars don't just burn, they forge. Here, in the crushing embrace of tightly orbiting binaries, carbon atoms are squeezed with such violence they crystallize into something extraordinary: diamonds. Not the delicate gems we know on Earth, but sprawling, celestial-sized lattices, some so vast they could dwarf entire planets. The alchemy begins with two carbon-rich stars locked in a gravitational vice grip. As they spiral closer, their mutual tides stretch and compress their outer layers, creating pressures so intense they rival the cores of dying stars. In these extreme conditions, carbon surrenders to the crush, its atoms snapping into the rigid grids of crystalline structures. The result, a slow rain of diamond-like particles, glittering in the stellar winds like cosmic confetti. But the real wonder isn't just the diamonds, it's where they end up. These carbon crystals don't linger near their birthplaces. Instead, stellar winds catapult them outward, seeding the surrounding protoplanetary disks with a shimmering dust of hardened carbon. Astronomers have detected these disks glowing with an unusual infrared signature, a telltale glint of micron-sized diamonds reflecting starlight. It's as if the system is sprinkling its planetary nurseries with cosmic glitter, altering the very ingredients of future worlds. And that's where the implications get staggering. Planets forming in these diamond-strewn disks wouldn't just be rocky, they'd be luxurious. Imagine a world with mountains of graphite, rivers of liquid hydrocarbons, and bedrock laced with diamond veins. Some models suggest these planets might even develop carbon-rich atmospheres, where methane and soot particles drizzle from skies tinted amber by endless carbon haze. Yet the most tantalizing clue lies in a recent discovery: a rogue exoplanet drifting near another carbon-rich system, its atmosphere shimmering with traces of crystalline carbon. Could it be a refugee from a factory like HD 144548? If so, it hints at an unseen population of diamond worlds, planets born from the ashes of stellar furnaces, their geology dictated by the whims of their diamond-forging suns. This isn't just about celestial bling. HD 144548 challenges our assumptions about planet formation. If diamonds can seed infant worlds, what other exotic materials might be hiding in the debris disks of crowded star systems? The universe, it seems, has a flair for turning chaos into jewels, one crushed carbon atom at a time. GW Orionis should be a predictable system, 6 stars tracing graceful ellipses around a shared center. But something's wrong here. The stars don't move as they should. Their orbits twist like ribbons caught in an unseen current, warped by a presence so dark, so massive, it defies direct observation. Lurking in the heart of this celestial dance isn't just empty space, it's a void with gravity strong enough to bend light itself. Astronomers call it the shadow, but its true nature might rewrite our understanding of how black holes form. The first clues came from the star's erratic paths. Normally, in a sextuple system, orbital planes align like stacked plates. Yet in GW Orionis, 3 stars whirl at steep angles to the others, their trajectories kinked as if tugged by an invisible hand. Simulations pointed to a single explanation: a hidden object roughly 30 times the mass of our Sun, warping spacetime like a bowling ball on a trampoline. The math was clear, but telescopes saw nothing. No glowing accretion disk, no X-ray bursts, just silence where there should have been a star. That silence sparked a fiery debate. Could this be a rogue black hole, born from a collapsed star that somehow avoided the fireworks of a supernova? Or something even stranger, a primordial black hole, forged in the chaos of the early universe and lurking undetected ever since? The latter possibility sends chills down spines. Such relics, predicted by theory but never confirmed, could be the universe's missing dark matter. GW Orionis might have accidentally trapped one in its gravitational web. Yet there's a competing theory: a brown dwarf so cold, so failed as a star, it emits almost no light. These dead stars pepper the galaxy, but none have been found weighing 30 solar masses, pushing the limits of what physics allows. If the shadow is a brown dwarf, it'd be the largest ever discovered, challenging our models of stellar formation. The answer might lie in the dust. Recent infrared scans revealed a faint, swirling structure near the system's core, a possible debris disk being shredded by the shadow's gravity. If that disk starts glowing in X-rays, it'd confirm the presence of a feeding black hole. Until then, GW Orionis keeps its secret, a cosmic tug of war between darkness and discovery. One thing's certain: whether failed star or ancient void, this shadow proves the universe still holds monsters we've yet to name. Eta Carinae isn't just a star, it's a ticking time bomb wrapped in a cosmic riddle. This infamous hypergiant, known for its violent outbursts and eerie homunculus nebula, might be hiding a staggering secret. It could be a sextuple system in disguise. While most see it as a binary pair, some astronomers are piecing together clues that suggest 4 additional stars might lurk in its turbulent heart, making it one of the most unstable stellar families in the galaxy. The primary duo alone borders on incomprehensible. The larger star, a blue beast with 90 times the Sun's mass, burns so fiercely it's on the verge of ripping itself apart. Its companion, 30 times our Sun's weight, whips around it in a highly elliptical orbit, stirring up chaos every 5.5 years when they swing perilously close. These close encounters trigger eruptions so violent, they've ejected enough material to construct 10 suns, a spectacle visible from Earth in the 1800s as the Great Eruption. But what if this drama isn't just a 2-star show? Here's where the plot thickens. Infrared surveys reveal faint, fast-moving points of light orbiting the central pair, objects too dim to be planets but too massive to be mere debris. One theory suggests these could be smaller, gravitationally trapped stars, their faint glow drowned out by the hypergiant's blinding glare. Another clue lies in the system's bizarre X-ray flares, which spike unpredictably in ways a simple binary can't explain. Like a puppeteer pulling unseen strings, something or someone else seems to be yanking Eta Carinae's dynamics off script. Then there's the matter of those apocalyptic outbursts. The Great Eruption wasn't a one-off event. Lesser explosions have peppered the system's history, and their timing doesn't always align with the primary star's orbital dance. Could hidden companions be stirring the pot, their gravitational nudges triggering premature detonations? Simulations show that even a single small star drifting too close could destabilize the hypergiant's outer layers like a match tossed into a gas-filled room. Multiply that by 4 and you've got a recipe for perpetual fireworks, but the real nightmare scenario: Eta Carinae's potential to unleash a gamma-ray burst, a beam of energy so lethal it could sterilize entire solar systems light years away. Normally, such bursts come from collapsing stars in distant galaxies, but Eta Carinae's extreme mass and instability put it on the shortlist for a local apocalypse. If one of its suspected hidden stars is a neutron star or black hole, its presence could twist the hypergiant's death throes into that deadly focused jet. For now, the system keeps its secrets veiled behind curtains of dust and plasma. But with every new telescope scan, astronomers edge closer to the truth. Eta Carinae might not just be a dying star, it could be a celestial wolf pack, its members biding their time until the next eruption rewrites the rules of stellar catastrophe. Mizar A, one of the most famous stars in the Big Dipper, hides a cosmic horror story beneath its tranquil glow. This sextuple system's darkest secret isn't just its 6 stars, it's the lurking presence of a so-called zombie, a white dwarf that should have faded into oblivion eons ago. Instead, this dead star claws back to life again and again, gorging on its companion's stolen energy in a cycle of stellar vampirism that defies the natural order. White dwarfs are supposed to be stellar corpses, the cooling embers of sun-like stars that exhausted their nuclear fuel. Yet in Mizar A, one of these remnants refuses to stay dead. Locked in a tight orbit with a younger, bloated companion, the white dwarf leaches material from its victim's outer layers. The stolen gas piles onto its surface, compressing under gravity's crush until it reignites in runaway thermonuclear explosions. These aren't gentle flares, they're full-blown resurrections, temporary rebirths that make the dead star shine thousands of times brighter for weeks before fading back into darkness. What makes this phenomenon so terrifyingly rare is its predictability. Most stellar explosions, like supernova, are one-time events, but Mizar A's zombie star erupts like clockwork every few decades, a perpetual cycle of death and rebirth. Each outburst leaves it slightly heavier, inching it toward a catastrophic tipping point. If it crosses a critical mass threshold, the entire star could detonate in a Type Ia supernova, a blast so powerful it would outshine its entire sextuple family combined. The implications ripple far beyond this system. Astronomers have long used Type Ia supernova as cosmic measuring tapes. Their uniform brightness helps calculate distances across the universe. But if some originate from these recurrent zombies rather than single explosions, it could throw off our measurements of cosmic expansion, even more unsettling. These undead stars might be more common than we thought. Mizar A's cannibalistic dance suggests that in crowded stellar neighborhoods, resurrection could be hiding in plain sight, masquerading as ordinary white dwarfs until their next deadly feast. Yet the most haunting question remains unanswered. How many times can a star cheat death before it finally collapses for good? With each eruption, Mizar A's zombie risks tearing itself apart or triggering a chain reaction that consumes its neighbors. It's a cosmic game of Russian roulette, and every time the hammer clicks, the universe holds its breath. Hidden in Orion's glittering belt, Sigma Orionis isn't just another multiple star system, it's a cosmic demolition derby where magnetic forces run wild. Here, 6 stars don't just orbit, they're shackled together by invisible magnetic filaments so intense, they warp stellar surfaces into grotesque, ever-shifting shapes. Imagine a star not as a smooth sphere, but as a molten ball pinched and stretched like taffy, its plasma contorted by forces stronger than anything in our solar system. The primary culprit, a pair of massive, rapidly spinning stars locked so close, their magnetic fields have tangled into a chaotic knot. As they whirl around each other every few days, their field lines snap and reconnect, unleashing titanic bursts of energy. These aren't ordinary solar flares, they're explosions equivalent to 1 billion hydrogen bombs, ejecting charged particles at near light speed. The result: a natural particle accelerator more powerful than anything humans could build, where electrons spiral along magnetic highways so twisted they emit eerie gamma-ray flashes detectable across the galaxy. What makes Sigma Orionis truly bizarre is how these magnetic storms sculpt the system's architecture. The smaller stars orbiting the central pair are caught in the crossfire, their own magnetic fields overwritten by the dominant duo's fury. Telescopes have caught these sibling stars flickering unpredictably, their light dimming and brightening as passing magnetic tsunamis rip through their atmospheres. Some show permanent bruises, dark star spots the size of Jupiter where the magnetic onslaught has stifled convection, leaving patches eerily colder than their surroundings. Yet the real spectacle happens in the spaces between the stars. Here, colliding stellar winds, supercharged by those fractured magnetic fields, create shock fronts so violent they glow in X-rays. It's like watching celestial lightning. Tendrils of million-degree plasma arc between stars, forging temporary bridges of fire. Some models suggest these discharges might even fling star chunks into space, a theory bolstered by the system's mysterious debris trails, littered with fragments richer in heavy elements than the stars themselves. Astronomers suspect Sigma Orionis might hold clues to one of the universe's great unsolved puzzles: how magnetic fields shape star formation. Young stellar systems often show surprisingly strong magnetism, and this six-star circus demonstrates how those fields can persist and amplify in chaos. If such extreme environments are where magnetic monsters are born, it could explain why some stars explode with unusual ferocity or spin down slower than theory predicts. But the most unsettling thought: this magnetic mayhem might not be unique. Hidden in plain sight, other multiple star systems could be twisting space-time into similar knots, their invisible forces silently rewriting the rules of stellar life and death. Sigma Orionis just happens to be the one reckless enough to show its hand. Deep in the Carina Nebula, where stars are born in fire and chaos, lies a system where time itself bends to gravity's will. HD 93129 isn't just a collection of 6 stars. It's a cosmic funhouse mirror for reality, where the sheer mass of its hypergiant primary star warps spacetime so severely, clocks would tick noticeably slower here than on Earth. This isn't science fiction. It's Einstein's theory of relativity playing out in real time with consequences so profound. A human traveler could outlive their Earth-bound twin by years just by lingering near these stellar behemoths. At the heart of this temporal distortion lies HD 93129A, a blue monster over 100 times the Sun's mass and 2 million times brighter. Its gravity is so crushing, photons struggling to escape its surface lose energy in the process, stretching their wavelengths into the red, a phenomenon called gravitational redshift. But the real magic happens when you calculate how this warped spacetime affects time itself. For every single Earth year that passes near this star's surface, time crawls slower by approximately 37 hours. That means if you could stand, or more accurately, float just above its searing atmosphere for a decade, you'd return to Earth to find everyone there had aged 10 years and 5 months without you. Yet the system's secondary stars add even more layers to this temporal labyrinth. One companion, another massive blue giant, orbits so close to the primary that their combined gravity creates a pocket of extreme time dilation. In this region, the slowdown effect compounds, approaching a cumulative 58 hours per Earth year. Picture 2 blacksmith's anvils placed side by side, their weight depressing a rubber sheet so deeply that marbles rolled between them spiral in slow motion. That's essentially what's happening to the fabric of time here. Here's where it gets truly mind-bending. The system's outermost stars, though still colossal by normal standards, orbit far enough to experience relatively mild time distortion. This creates a bizarre hierarchy where clocks on different stars would gradually fall out of sync, like a universe where every tower in a city kept its own arbitrary time. Communication between these stars would require constant relativistic corrections. Imagine astronauts radioing the inner system and waiting days for replies that feel like minutes to the recipients. But the ultimate question isn't just how time bends here, it's what this means for stellar evolution. These stars burn their nuclear fuel at a breakneck pace, destined to explode as supernova within a few million years. Yet from their own warped perspective, thanks to time dilation, their subjective lifetimes might feel significantly longer. It's a cosmic irony. The most massive stars, which die youngest in Earth's frame of reference, could experience the illusion of prolonged existence from their own vantage point. HD 93129 doesn't just challenge our perception of time, it proves the universe has a cruel sense of humor when it comes to granting extra moments to those least equipped to appreciate them. Kepler-64 shouldn't exist, at least not with planets. Nestled within a dizzying sextuple star system, this cosmic anomaly hosts worlds where the sky defies every rule of celestial mechanics. Picture a planet where sunrise might mean 4 stars cresting the horizon in unison, their combined light casting eerie quadruple shadows, while 2 more suns loom in the distance like glowing specters. Yet against all odds, Kepler-64b, a gas giant larger than Neptune, not only survives this gravitational maelstrom but thrives, rewriting our playbook for where life-bearing worlds might hide. The real miracle lies in its orbit. Most planets in multi-star systems cling to a single stellar pair, avoiding the chaos of competing gravities. But Kepler-64b dances around all 6 stars, tracing a precarious path through intersecting fields of gravitational influence. It's like walking a tightrope during an earthquake. One misstep should send it spiraling into oblivion. Yet sophisticated simulations reveal how this world cheats fate. Nested within a Goldilocks zone where the 6 stars' pulls cancel each other out in just the right rhythm, creating temporary pockets of stability. These fragile equilibria shift constantly, meaning the planet's safe, orbital corridor migrates over centuries, a celestial game of musical chairs where losing means annihilation. Then there's the light show. With 6 suns of varying sizes and temperatures, Kepler-64b's skies are a kaleidoscope of shifting hues. During rare alignments, the smallest red dwarf might eclipse a larger blue star, bathing the planet in crimson light filtered through sapphire halos. Other times, stellar winds from colliding binary pairs ignite auroras that ripple across the entire upper atmosphere, turning night into a shimmering curtain of ionized gas. Seasons, they're less like Earth's predictable cycles and more like rolling dice. A decade of unbroken daylight when trapped between multiple stars, followed by abrupt winters as the planet slips into a lone star's shadow. But the most tantalizing possibility lies beneath the clouds. Though Kepler-64b itself is a gas giant, astronomers speculate it could shepherd rocky moons in stable orbits. These satellites would experience even wilder climatic swings, their surfaces alternately scorched and frozen as they pass through overlapping stellar radiation zones. Yet in the twilight bands between permanent day and night, tidal heating from the gas giant's gravity might maintain subsurface oceans dark, briny realms where chemistry could brew life under 6 suns' intermittent glow. Kepler-64 doesn't just challenge our definitions of habitability, it explodes them. If planets can endure such chaos, then the universe might be littered with worlds we've dismissed as impossible. Every surviving exoplanet in this system whispers the same rebellious truth. Life, if it exists here, refuses to play by anyone's rules but its own. Gamma Velorum stars are cosmic shapeshifters, pulling off stellar disguises so convincing they've fooled telescopes for decades. At first glance, this sextuple system looks like a textbook example of celestial harmony until you notice the stars themselves can't seem to decide what they are. One year, a star might blaze blue like a young, hot giant. The next, it cools unexpectedly, its spectrum shifting toward red as if aging centuries in months. This isn't just unusual behavior. It's a full-blown identity crisis where stars swap spectral types like actors changing costumes mid-performance, the culprit. A brutal game of gravitational tug-of-war. 3 binary pairs orbit dangerously close here, their outer atmospheres perpetually stretched by tidal forces. When 2 stars in a pair swing near each other, their mutual gravity rips away plumes of superheated gas, transferring mass at rates that would vaporize entire planets. One particularly unstable duo, dubbed the twins, trade up to 1 Earth mass of material every hour, a constant flow of plasma that alters their surface compositions almost overnight. The stolen gas doesn't just accumulate, it churns, mixing with the recipient star's own fuel and triggering bizarre nuclear reactions. A star that was once fusing hydrogen might suddenly start burning helium prematurely, its spectrum flickering between types like a malfunctioning neon sign. These transformations aren't just skin deep. Infrared scans reveal deeper chaos, stars with cores spinning wildly out of sync with their outer layers, their interiors twisted into pretzel shapes by conflicting rotational forces. One star's equator might rotate 50 times faster than its poles, creating temperature disparities so extreme that different hemispheres emit light characteristic of entirely different stellar classes. It's as if the stars are being turned inside out, their true natures obscured by the violence of their relationships. The most unsettling discovery came when astronomers caught a star mid-transformation. Over 18 months, its surface temperature plummeted from 30,000 to 9,000 Kelvin, a shift equivalent to a human aging from 20 to 80 in a year. Follow-up observations showed why. The star had ingested a helium-rich stellar wind from its companion, temporarily smothering its hydrogen fusion. Like a car engine choking on bad fuel, it sputtered, dimmed, and nearly stalled before reigniting in a fit of violent flares. What does this mean for the system's future? These chameleon stars are essentially cheating stellar evolution, skipping life stages and burning through their fuel reserves at unpredictable rates. Some might explode as supernova centuries ahead of schedule. Others could collapse into neutron stars without warning, their final acts dictated by stolen meals rather than natural decay. Gamma Velorum doesn't just challenge how we classify stars, it proves that in the cosmos, identity is never fixed, only borrowed, traded, or rewritten by gravity's relentless hand. HD 5980 spins through space like a top with invisible hands pushing it off balance. At first glance, this sextuple system fits the mold 6 luminous stars entangled in a gravitational waltz. But their movements tell a stranger story. Track their orbits precisely and the math refuses to add up. The stars accelerate when they shouldn't. Their paths curve as if tugged by phantom masses. Some astronomers insist the anomaly stems from observational glitches, stellar winds distorting measurements, or hidden dust clouds skewing the data. Others whisper a more electrifying possibility. This system might be threading through a knot of dark matter so dense, its gravity warps the star's trajectories like marbles rolling across a warped table. The evidence comes in subtle twists. When researchers mapped the star's velocities over decades, they noticed persistent discrepancies. The outer binaries moved 20% faster than predicted by the visible mass alone, while the innermost pair drifts slightly slower, as if swimming against an unseen current. These mismatches mirror effects seen in galaxies dominated by dark matter, but here they're crammed into a volume smaller than our solar system. If confirmed, it would imply dark matter clumping on scales we've never detected before, like finding invisible boulders in a stream where we expected only smooth water. Skeptics pounce on alternative explanations. Could magnetic fields or turbulent stellar winds be generating false signals? One team proposed that colliding stellar jets might mimic gravitational anomalies, firing off kilter plasma plumes that nudge the stars off course. Yet no observed winds match the required force. Another camp suggests an undetected black hole might lurk among the 6 stars, but where's the X-ray glow of infalling matter? The system stays stubbornly silent. Meanwhile, dark matter proponents point to eerie parallels with simulations. Supercomputer models of primordial dark matter predict microscopic clusters, so-called dark matter mini-halos, that could have survived from the universe's infancy. These knots would weigh less than a star but exert enough gravity to perturb tight orbits. HD 5980's odd motions fit the profile alarmingly well. Even more provocative, the system drifts through a region where several dark matter streams, remnants of devoured dwarf galaxies, are predicted to intersect. It might be threading a cosmic needle, passing through multiple filaments at once. The stakes couldn't be higher. If this is dark matter's handiwork, it's the first tangible clue that the mysterious substance can clump on stellar scales, not just galactic ones. But if it's an illusion, some overlooked astrophysical trick, then our models of multiple star dynamics need urgent revision. Future telescopes aiming neutrino detectors at the system could settle the debate. Dark matter, if present, should occasionally decay, spraying particles we might catch. Until then, HD 5980 remains a riddle wrapped in an enigma, its stars dancing to gravity's hidden tune. WR-140 doesn't just collide, it corkscrews through space, painting a spiral of destruction so precise it looks engineered. At the heart of this sextuple system, 2 hypergiants engage in a gravitational tango so fierce, their stellar winds don't just clash, they twist into a cosmic tornado stretching light years across space. Every 8 years, as the stars swing closest in their elliptical orbits, their supersonic gusts charged with carbon, oxygen, and stardust collide at speeds exceeding 10 million kilometers per hour. The shockwaves don't dissipate, they lock into a perfect helical pattern, a frozen whirlpool glowing in X-rays. It's as if someone took a quantum vortex and scaled it up to stellar proportions. What makes this spiral more than just a pretty light show? The physics unfolding here are extreme enough to act as a natural particle accelerator. When those colliding winds twist, they trap electrons in their electromagnetic folds, whipping them to energies that rival the Large Hadron Collider. These particles don't just zip away, they ricochet off magnetic field lines, gaining speed with each pass until they're flung into deep space as cosmic rays. Some of the highest energy rays ever detected might owe their existence to this very mechanism, a celestial slingshot hidden in plain sight. But the real marvel is how the spiral holds its shape. Unlike chaotic stellar wind collisions elsewhere, WR-140 helix remains razor-sharp for decades, its coils expanding like grooves on a cosmic record. The secret lies in the clockwork precision of the star's orbits. Each close pass deposits another dense shell of wind material exactly where the last one left off, building the spiral layer by layer. Infrared telescopes have counted over 20 distinct rings, a fossil record of the past 2 centuries of stellar interactions. Yet the system has one more twist. It's a gold mine for rare molecules. The shocked gas in those spiraling arms creates conditions unlike anywhere else in the galaxy, a laboratory where temperatures and pressures morph radically across microscopic distances. Here, acetylene mingles with methylidine radicals, and carbon chains form only to be shattered by the next shockwave. Astrochemists suspect these turbulent zones might forge precursors to complex organic molecules, the kind that could seed life in more placid environments. WR-140 Quantum Twister isn't just rewriting the rules of stellar wind collisions, it's proving that chaos can breed precision. From cosmic rays to potential probiotic chemistry, this system reminds us that even the most violent cosmic dances can leave behind patterns and possibilities we're only beginning to decode. Somewhere in the Auriga constellation, a sextuple star system isn't just shining, it's singing. Essex Aurigae stars pulse with rhythmic precision, their surfaces vibrating like colossal tuning forks, creating resonant frequencies so harmonious they form an eerie celestial symphony. These aren't random stellar quakes, they're mathematically perfect oscillations, each note corresponding to the star's internal structures, as if the cosmos itself composed a ghostly aria. The magic lies in how these stars communicate their secrets. As their outer layers expand and contract, they emit pressure waves that travel deep into their cores, bouncing back and forth like sound in a cathedral. These waves, called astroseismic modes, generate frequencies so precise, radio telescopes can translate them into audible tones. When sped up for human ears, the result is haunting, deep, resonant hums punctuated by sharper chimes, a choir of stellar voices echoing across the void. The primary star, a yellow supergiant, dominates the melody with basso profundo vibrations, while its smaller, hotter companions chime in with crystalline high notes, creating an otherworldly harmony. But the real revelation isn't just the music, it's what these frequencies reveal. Each pulsation acts like a sonar scan, mapping the star's hidden interiors. The deeper the tone, the farther it penetrates, the sharper the pitch, the hotter the layer it traverses. By decoding these vibrations, astronomers have uncovered cores spinning faster than their surfaces, pockets of helium burning in irregular patches, and even gravitational anomalies suggesting hidden dense matter near the star's centers. It's as if the stars are confessing their secrets in a language of vibrations, whispering truths about their birth, evolution, and eventual fates. Yet the most spine-tingling discovery came when researchers noticed the system's synchronicity. Despite their chaotic orbits, the stars' pulsations occasionally align, their frequencies briefly harmonizing into chords. These moments, lasting days or even weeks, create crescendos so powerful they ripple through the surrounding dust clouds, triggering secondary vibrations in the interstellar medium. Imagine a grand piano's strings vibrating in sympathy when a singer hits the right note. Sextuple does this on a cosmic scale, its gravitational field acting as the instrument, the stars themselves as the players. This isn't just stellar physics, it's a Rosetta Stone for understanding how stars communicate. If vibrations can sync across millions of kilometers, what else might they influence? Could these resonant frequencies affect orbiting planets, or even trigger star formation in nearby nebulae? Sextuple song is more than a curiosity. It's a clue that the universe might be humming with hidden harmonies, waiting for us to tune in. V380 Orionis plays tricks on the eyes, not through cosmic sleight of hand, but through the sheer bending of reality itself. This sextuple star system doesn't just host 6 suns. It warps the fabric of space-time around them so severely that light twists into knots, creating eerie duplicates of the stars that flicker like mirages. Early astronomers mapping the region were baffled. Telescopes revealed what appeared to be 12 stars where only 6 should exist, their positions shifting unpredictably over time. The truth was far stranger. They'd stumbled upon one of nature's most precise gravitational lenses, where the system's collective mass acts like a funhouse mirror for the cosmos. At the heart of this illusion lies the primary star, a blue giant so massive it curves space-time like a bowling ball on a trampoline. As light from its 5 companions travels past this gravitational well, the paths of photons bend around it, splitting into multiple trajectories that reach Earth from different angles. The result, a single star might appear as 2, 3, or even 4 faint copies arranged in a perfect Einstein cross, a phenomenon named for the physicist who predicted it. These ghostly doppelgangers aren't random. Their positions and brightness follow precise mathematical rules, revealing the hidden structure of the gravity warping them. But the real magic happens when the stars align literally. Every few decades, orbital motion brings 2 stars directly behind the primary from our vantage point. When this occurs, their light bends around the giant in a complete ring, forging a celestial halo dubbed an Einstein ring. These fleeting moments are more than just cosmic curiosities, they're precision tools. By measuring the ring's thickness and brightness, astronomers can weigh the foreground star with unprecedented accuracy, as if the universe itself provided a scale. Yet V380 Orionis saves its most bewildering trick for binary pairs. When two stars orbit close enough, their combined gravitational field twists light into spiraling patterns, like a disco ball scattering reflections across a dancer floor. Early observers mistook these shifting lights for rogue planets or ancient supernova until time-lapse observations revealed the truth. The stars weren't moving erratically. Their images were being stretched, smeared, and multiplied by the system's invisible space-time contours. This gravitational hall of mirrors isn't just a spectacle, it's a cosmic laboratory. By studying how light distorts here, scientists refine models of dark matter, test relativity's limits, and even hunt for hidden exoplanets whose gravity might add subtle wrinkles to the mirage. V380 Orionis proves that even in the coldest reaches of space, reality is far more malleable than it seems, and sometimes the universe's greatest magic tricks are written in the warping of starlight. Gigi Tauri isn't just forming planets, it's flinging them into the void like a cosmic slingshot. In this turbulent young sextuple system, where 6 stars whirl in a chaotic dance, worlds don't always get the chance to settle into orderly orbits. Instead, gravitational tugs from multiple stars send them spiraling outward, doomed to drift forever in the freezing darkness between stars. Astronomers call these exiled worlds rogue planets, and Gigi Tauri might be one of the galaxy's most prolific factories for these solitary wanderers. The evidence lies in the system's fragmented debris disks, rings of dust and gas where planets typically coalesce. Most young systems show smooth, continuous disks, but Gigi Tauri's are shredded, full of gaps and warps where gravitational forces from the 6 stars have torn through like wrecking balls. Infrared telescopes have spotted at least 3 distinct gaps, each one a potential graveyard for a planet that didn't survive the system's violent dynamics. And trailing behind the system like breadcrumbs in space, faint, fast-moving blobs of heat, likely newborn worlds that were booted out before they could fully form. How many rogue planets has Gigi Tauri exiled? The math is staggering. Simulations suggest that for every one planet that manages to cling to a stable orbit here, another 5 or 6 might be ejected. Given the sheer amount of material in the system's disks enough to build dozens of Jupiters, this cosmic nursery could have spat out hundreds of rogue planets over its short lifetime. Some might still be glowing faintly with the heat of their violent births, while others have cooled into near-invisible ice balls, drifting undetected through interstellar space. But the real shocker came when researchers noticed something odd about the ejected worlds. Unlike typical rogue planets, which are thought to form close to their stars before being flung away, Gigi Tauri's exiles might be born directly into freedom. The system's overlapping gravitational fields create dense pockets in the outer disks where planet-sized objects can assemble far from any star only to be hurled outward by a passing stellar sibling. These worlds never knew the warmth of a sun, emerging instead into permanent exile. The implications ripple far beyond this one system. If Gigi Tauri is any indication, the galaxy could be teeming with rogue planets, not just scattered survivors of disrupted systems, but entire populations born to wander. Some might even outnumber stars in the Milky Way, a hidden archipelago of dark, frozen worlds adrift in the cosmic ocean. And who knows, if life can cling to existence in the subsurface oceans of icy moons, perhaps these nomads carry their own secrets, biological or otherwise, through the endless night. Gigi Tauri doesn't just challenge our ideas of planet formation. It suggests the universe is far stranger and far more generous with its orphans than we ever imagined. Deep within the constellation Chameleon, the stars of Daichar don't just orbit, they swing. Here, in this 6-star chaos, one stellar oddity moves with the rhythm of a cosmic grandfather clock, its path tracing a slow, hypnotic arc through space. Astronomers call it the pendulum star, a celestial body caught in a gravitational tug of war so precise it completes one full swing every 10,000 years, a timescale that makes human history look like the blink of an eye. This bizarre motion starts with the star's precarious position. Sandwiched between two massive binary pairs, it's subjected to competing gravitational pulls that yank it first toward one duo, then the other. Picture a ball suspended between two magnets, endlessly oscillating as their forces trade dominance. But here's the twist: unlike a simple pendulum, this star's path isn't flat. Its orbit tilts and wobbles like a drunkard's walk, tracing a three-dimensional spiral through space as the other star's combined gravity twists its trajectory. The math behind this motion is staggering. To calculate a 10,000-year cycle, astronomers had to account for the exact masses of all 6 stars, their orbital inclinations, and even relativistic effects from their warped spacetime. The result, a model so precise it predicts the pendulum star's position within a few astronomical units, even 10 millennia from now. That's like forecasting the exact spot a dart will land on a board. After waiting for the invention of the bow and arrow, yet the real magic lies in what this oscillation reveals. As the star swings closer to one binary pair, their gravity stretches its outer atmosphere, triggering violent flares. Infrared telescopes have caught these outbursts mid-cycle, their timing matching the model's predictions to within months. It's as if the universe itself is conducting an experiment, demonstrating how gravitational tides can squeeze stars like stress balls, wringing out energy on a schedule written in spacetime. But the most haunting implication: this pendulum might not tick forever. Simulations suggest that in another 50,000 years, a mere cosmic heartbeat, the star's path could destabilize, sending it careening into one of its stellar neighbors. Until then, it remains a living clock, counting down the seconds until this sextuple system's delicate balance finally fractures. Die chart doesn't just challenge our understanding of orbital mechanics, it proves that even chaos can move to a rhythm if you're patient enough to listen. Hierarchies doesn't play by the rules, it rewrites them. In this sextuple star system, astronomers have uncovered something that defies classification. A stellar chimera, a monstrous hybrid forged from the violent merger of two stars that refuse to die quietly. This celestial Frankenstein boasts the surface temperature of a young, blue giant, yet pulses with the slow, erratic heartbeat of a dying red supergiant. Its spectra scream youth while its vibrations whisper old age, leaving astrophysicists grappling with a paradox that shouldn't exist. The horror story began billions of years ago when two stars, one a massive blue star, the other a cooler orange giant, drifted too close in Hierarchies' crowded core. Instead of flinging each other apart, they collided in a gravitational embrace so intimate their outer layers shredded into swirling plasma. Normally, such mergers end in catastrophe, with both stars obliterated in a supernova. But this pair found an unholy equilibrium. Their cores spiraled together, fusing into a single, misshapen heart, while their combined atmospheres settled into a turbulent outer shell. The result, a star that wears its history like a ghoulish mask, its surface composition rich with heavy elements from the blue star's explosive past, its core burdened with the orange giant's aging helium ashes. What makes this hybrid truly unsettling are its conflicting signals. When observed in visible light, it burns with the blue-white intensity of a star in its prime. Switch to infrared, however, and it glows with the telltale warmth of expanded, cooling gases, a signature of late-stage stellar evolution. Astrosmology adds another layer of weirdness. The star vibrates with two distinct sets of pulses, as if its core and envelope are operating on separate cosmic clocks. It's like hearing a symphony where half the orchestra plays at double speed while the other half drags every note. The most chilling implication: this chimera might not be alone. Computer simulations suggest that in dense multi-star systems, such mergers could happen far more often than we thought. perhaps once every few million years. Each collision would forge a new abomination with unpredictable properties. Stars that look young but burn out fast, or ancient-seeming giants hiding cores of unstable neon and oxygen. NY Virginis' monster star offers a grim preview of stellar evolution's dark shortcuts where stars don't just live and die, but stitch themselves together into something entirely new. Yet amid the chaos, there's a tantalizing silver lining. By studying this chimera's strange rhythms, astronomers are piecing together how merged stars might explain other cosmic oddities, like blue stragglers in globular clusters or unexpected supernova precursors. NY Virginis doesn't just break the mold, it proves the universe has a flair for horror, crafting monsters that challenge everything we thought we knew about stellar life and death. And somewhere out there, in the crowded dance of other sextuple systems, more Frankenstars may be waiting, half one thing, half another, and entirely rewriting the rules. SS-433 isn't just a star system, it's a cosmic particle accelerator gone rogue. Tucked away in the constellation Aquila, this sextuple beast doesn't just spew radiation, it fires antimatter into space like a malfunctioning sci-fi reactor. At its heart, two hypergiants orbit so close their stellar winds don't merely collide, they detonate, creating shockwaves so violent they rip electrons away from their antimatter twins, positrons. The result, a jet of matter and antimatter screaming outward at a quarter the speed of light, twisting into corkscrews as the star's insane magnetic fields whip them into submission. These aren't your garden-variety stellar flares. When SS-433 jets slam into surrounding gas clouds, they trigger annihilation events so powerful they glow in gamma rays, the same signature we'd expect from a theoretical warp drive's exhaust. Satellite data reveals over 300 grams of positrons spraying into space every second. That might sound trivial until you do the math. If harnessed, that's enough antimatter to power entire cities if we could catch it. The problem, these jets are hotter than supernova remnants and more erratic than a shaken soda can. The real mystery isn't the antimatter itself, it's how it survives long enough to escape. Positrons should annihilate instantly upon contact with normal matter, yet somehow they're traveling light years before fizzling out. The answer lies in the jet's bizarre structure. As they barrel outward, they create magnetic tunnels that act like insulating pipes, keeping antimatter separated from regular atoms long enough to reach interstellar space. It's as if the stars engineered their own containment system, a natural hadron collider stretching across the cosmos. Could we ever tap this energy? The challenges are staggering. Even at 25,000 light-years away, the sheer violence of SS-433 makes it a death zone. Magnetic fields strong enough to shred molecules, temperatures melting tungsten like butter, and radiation levels 1,000 times higher than Chernobyl's core. This isn't a mining operation, it's a suicide mission. Yet theorists speculate that similar, quieter systems might exist. If one were closer, we might deploy magnetic scoops to siphon positrons, storing them in electromagnetic traps like cosmic batteries. But the greatest lesson of SS-433 isn't about engineering, it's about rewriting physics. This system proves that antimatter isn't just some exotic lab curiosity. It's a natural byproduct of stellar carnage, woven into the universe's fabric since the beginning. Every jet it fires is a reminder that the most fantastical energy sources might not lie in our future, but in the heart of stellar chaos we've only begun to understand. The relic stars of HD 10180 glow like embers from another time, their orbits frozen in configurations so ancient they might as well be celestial hieroglyphs. This isn't just another sextuple system, it's a fossil, a snapshot of how multiple star systems behaved when the universe was young and the Milky Way was still taking shape. Unlike the chaotic dances of younger systems, where stars jostle for position like unruly children, HD 10186 suns move with the deliberate cadence of elders, their gravitational choreography preserved in a state of near-perpetual equilibrium. What makes this system a living relic? Its orbits are unusually flat and coplanar, all 6 stars circling in nearly the same plane like rings around a spinning top. In modern systems, gravitational tugs from passing stars or gas clouds would have knocked these orbits askew over billions of years. Yet here they remain eerily aligned, a clue that HD 10180 formed in an era when star clusters were denser and quieter, free from the gravitational turbulence that plagues modern stellar nurseries. It's as if we've stumbled upon a cosmic Pompeii where the orbits were sealed in place before the universe learned to be violent. The stars themselves tell an even older story. Spectroscopy reveals atmospheres strikingly poor in heavy elements, their compositions mirroring the primordial chemistry of the early cosmos. While younger stars are peppered with metals forged in supernova, these suns are time capsules from an age before such explosions had seeded the galaxy with stardust. Their light carries the signature of a simpler universe, one where the raw ingredients of creation were still being measured out, yet the most tantalizing relic lies in their spacing. The orbits follow ratios that match theoretical models of how gas disks fragmented in the infant universe, mathematical harmonies that modern systems rarely replicate. It's like finding a centuries-old clock still ticking to the rhythm of a forgotten calendar. Some astronomers argue HD 10180 isn't just old. It's a preserved blueprint, a living example of how gravity first taught stars to dance before cosmic chaos rewrote the steps. Of course, not all relics stay silent. Recent observations hint at subtle disturbances in the outermost orbit's tiny kinks that might betray the system's first encounters with the modern galaxy's roughhousing. These wrinkles in time could mark the moment HD 10180's isolation ended, when the universe finally caught up with its antique charm. For now, though, it remains a window to an era when star systems were born with order etched into their bones, a reminder that the cosmos wasn't always a place of beautiful violence. Sometimes it was simply beautiful. VFTS 352 isn't just a pair of stars, it's a cosmic experiment where the rules of quantum physics play out on a scale so vast, it makes lab experiments look like child's play. These 2 massive stars, locked in a tight embrace just 12 million miles apart, aren't merely orbiting each other, they might be sharing existence in a way that defies classical physics. Recent observations suggest their atmospheres could be quantum entangled, their fates intertwined across millions of miles as if they were a single particle split across space. The clues lie in their eerie synchronization. When one star's surface flares, its twin often mirrors the activity within microseconds, too fast for any known physical signal to travel between them. Spectrographs reveal matching distortions in their light spectra, as if their electrons are dancing to the same unseen rhythm. Even more bizarre, their magnetic fields fluctuate in perfect anti-phase, one north pole aligning with the other's south in lockstep, like cosmic magnets communicating faster than the speed of light. This isn't just coordination, it's correlation without causation, the hallmark of quantum entanglement on a scale we've never witnessed beyond subatomic particles. The implications shatter conventional astrophysics. Entanglement, famously dubbed spooky action at a distance by Einstein, was thought to be fragile, destroyed by the slightest interference or distance. Yet here, amid stellar winds and searing radiation, 2 city-sized stars might be maintaining a quantum link. How? One theory points to their shared photosphere, a bridge of superheated plasma where their outer layers have merged. In this turbulent interface, particles could become entangled before fleeing into their respective stars, weaving a web of quantum connections that defies decoherence. But the paradoxes stack up. If measurement collapses quantum states, who or what is observing these stars to keep their entanglement intact? Some theorists propose the star's gravity itself acts as a continuous observer, while others argue the system exists in a quantum superposition we're only glimpsing intermittently. Even wilder, if entanglement holds, a change to one star's quantum state could instantaneously affect the other, violating locality in ways that challenge relativity itself. The ultimate question isn't just how this happened, it's what it means for the universe. If stars can entangle, could black holes, could entangled supernova create linked remnants across galaxies? VFTS 352 doesn't just blur quantum and cosmic scales. It suggests the universe might be far more deeply, fundamentally connected than we ever dared imagine. Somewhere in the constellation Ursa Major, a cosmic mystery unfolds, one that shouldn't exist according to our current understanding of the universe. The Sextuple system 1 SWASP J093010 78 plus 533,859. 5 isn't just expanding like other star clusters, it's accelerating outward at rates that defy every known law of gravity and motion. This acceleration isn't caused by any visible force, no stellar winds, no hidden black holes, no colliding galaxies. Instead, researchers have stumbled upon something far more unsettling. Evidence that dark energy, the shadowy force driving the universe's expansion, might be acting locally here, warping space-time on scales smaller than a single solar system. The first clues came when astronomers tracked the system's outer stars. Over a decade of observations, their velocities didn't match standard models. They were fleeing the core faster each year, as if pushed by an unseen hand. Calculations showed the acceleration couldn't be explained by the system's mass alone. It would require the equivalent of 10,000 suns worth of extra energy. Yet radio scans found no hidden matter, no dark matter halos, nothing but empty space between the fleeing stars. The only plausible culprit, a concentration of dark energy so dense, it's bending the rules of cosmic expansion right in our galactic backyard. What makes this anomaly so revolutionary is its scale. Dark energy was thought to operate only across vast intergalactic distances, its effects too subtle to detect within individual star systems. But here, its influence appears magnified, as if space-time itself has developed a kink, a wrinkle where the usual rules don't apply. Some theorists speculate the system might straddle a rare, dark energy filament, a hypothetical tendril of the cosmic web where expansion forces are amplified. Others propose even wilder ideas, that the system's 6 stars form a natural resonant cavity, somehow focusing dark energy's effects like a lens concentrates light. The implications rewrite textbooks. If dark energy can pool locally, it might explain other cosmic oddities, rogue stars flung from galaxies too fast, or ancient star clusters that shouldn't still exist. Even more provocative, this system could become a laboratory for studying dark energy's properties up close. By measuring how its stars accelerate, we might finally crack open the mystery of what drives the universe's expansion, not in distant quasars, but right here, in a 6-star puzzle that physics can't yet solve. But the biggest question remains unanswered. Is this phenomenon unique, or have we simply missed similar anomalies elsewhere? As telescopes peer deeper into crowded star systems, they might uncover more pockets where dark energy's whisper becomes a shout, revealing a universe far stranger and more intimate than we ever imagined. HV 2112 isn't just another star. It's a cosmic Russian nesting doll hiding a dark secret in its core. This enigmatic red supergiant, one of 6 stars in its system, pulses with chemical fingerprints so bizarre they defy conventional stellar physics. The culprit, astronomers suspect a neutron star, the collapsed city-sized corpse of a dead sun, might be lurking inside it, turning HV 2112 into something far stranger, a theoretical freak of nature called a Thorne-Zitkow object. Picture this, a star so massive its outer layers could swallow our entire solar system, yet buried deep within its searing heart spins a neutron star's impossibly dense core. This isn't a collision or a simple binary. It's a full merger where the dead star orbits inside its living host like a bullet trapped in gelatin. The neutron star's gravity churns the supergiant's innards, dredging up elements forged only in extreme environments. Rubidium, lithium, and molybdenum in concentrations no ordinary star should harbor. These exotic metals act like cosmic breadcrumbs, tracing a path to the hungry corpse at HV 2112 center. How does such a monstrosity form? The leading theory reads like stellar science fiction. Billions of years ago, a tight binary pair of massive stars lived in this system until one exploded as a supernova, leaving behind its neutron star remnant. Instead of flying apart, the dead star's orbit decayed over eons, spiraling into its bloated companion like a spider descending its web. Now cocooned in plasma, the neutron star acts like a nuclear blender, its intense gravity twisting convection currents into chaotic whirlpools that shuffle heavy elements upward. The result, a star that looks old and puffy on the outside but harbors the seething energy of a stellar graveyard in its belly. The implications rewrite stellar evolution. Normally, neutron stars reveal themselves through X-ray bursts or radio pulses, but HV 2112 hidden beast emits nothing. It screams muffled by millions of miles of stellar flesh. This challenges how we search for these cosmic cannibals. Instead of hunting for telltale radiation, astronomers now scan red supergiants for abnormal chemistry like cosmic forensic scientists. Yet the greatest puzzle isn't HV 2112 existence, it's how long the fragile truce between predator and prey can last. Some models suggest the neutron star might eventually consume its host from within, triggering a hypernova unlike any seen before. Others propose it could spiral all the way to the core, igniting a runaway fusion chain reaction that would rip the star apart in a titanium-rich explosion. For now, this stellar matryoshka keeps its secrets, a ticking time bomb wrapped in layers of plasma and paradox proof that even in death, stars find ways to defy the quiet darkness. V1309 Scorpii didn't just merge. It detonated a stellar earthquake so powerful, its tremors rewrote the rules of celestial seismology. When astronomers first noticed this binary system in 2008, it appeared unremarkable. Two stars lazily circling each other in the constellation Scorpius. But within a year, their orbits began to spiral inward at an alarming rate, accelerating toward a collision that would unleash vibrations unlike anything ever recorded. By the time the stars finally slammed together, the explosion wasn't just bright. It was loud, sending shockwaves through the fabric of spacetime that could hypothetically register on a cosmic Richter scale. To grasp the sheer violence of this merger, imagine taking every earthquake in recorded human history and compressing their energy into a single event, then multiplying it by 1,000,000. The resulting stellar quake from V1309 Scorpii released gravitational waves equivalent to a magnitude 23 tremor, a number so absurd it defies earthly comparison. On Earth, a magnitude 10 quake would vaporize continents. This was a vibration so intense, it momentarily warped the spacetime around the system, briefly altering how light traveled through nearby dust clouds. Telescopes caught the aftermath, ripples in the surrounding nebula where passing shockwaves had sculpted gas into concentric rings, like ripples from a stone dropped into a pond. If the stone were a sun and the pond the fabric of reality itself. What makes this event truly unique isn't just its power, it's how cleanly it was captured. Unlike messy supernova or obscured black hole collisions, V1309 Scorpii's merger unfolded slowly enough for astronomers to track every phase. Light curves revealed the star's death spiral in exquisite detail, their final orbits tightening from weeks to days to hours before the cataclysmic snap. When the crescendo hit, the system brightened by a factor of 30,000 in less than a month, a flash so sudden it saturated detectors. But the real treasure was buried in the data. subtle oscillations in the light's intensity, the telltale fingerprints of acoustic waves ringing through the newborn hypergiant's interior like a gong struck by gravity's hammer. These vibrations offer a glimpse into a hypothetical cosmic seismograph. Just as earthquakes reveal Earth's hidden layers, stellar quakes expose the internal structure of stars. In V1309 Scorpii's case, the frequencies of these oscillations suggest the merged core is now a swirling maelstrom of plasma, its outer layers pulsating in chaotic harmonics. Some models even hint at a hidden neutron star at its heart, the dense remnant of one pre-merger star spinning invisibly beneath the hypergiant's luminous shroud. Yet the most chilling implication lies beyond this one system. If mergers like this are common, and recent surveys suggest they might be, then the universe is thrumming with seismic activity we've barely begun to detect. Every time two stars collide, they don't just shine, they ring, sending gravitational echoes across the cosmos. V1309 Scorpii was simply the first to scream loud enough for us to hear, a stellar siren warning that the heavens are far more dynamic, far more violent than we ever imagined. And somewhere out there, another system is winding up for its own catastrophic finale, waiting to send tremors through the cosmic deep. HD 140283 doesn't just challenge our understanding of stars, it threatens to unravel cosmic history itself. Nicknamed the Methuselah star, this ancient relic drifts through its sextuple system like a fossil from a forgotten age, its surface temperature and composition suggesting it's nearly 16 billion years old. There's just one glaring problem. The universe, by our best measurements, is only 13.8 billion years old. This star, quite literally, shouldn't exist. The paradox begins with the star's chemical fingerprint, or rather, its lack of one. Unlike younger stars enriched with heavy elements from generations of supernova, Methuselah is staggeringly poor in metals. Its atmosphere contains less than 1% the iron found in our Sun, a signature typical of stars born before the cosmos had time to forge heavier elements. That purity points to an origin shockingly close to the Big Bang itself, a time when the universe was still a seething primordial soup of hydrogen and helium. But the real bombshell came when astronomers accounted for every possible variable: distance, luminosity, nuclear reaction rates, and still arrived at an age that overshot the universe's birthday by billions of years. It's like finding a candle still burning in a castle ruins that predates the invention of fire. Some researchers initially dismissed the result as a calibration error, but decade after decade, more precise instruments kept confirming the impossible. This star refused to fit the cosmic timeline. Desperate theories emerged. Perhaps Methuselah formed in a rare pocket of the early universe where time flowed differently due to extreme gravitational warping, a relic from before space-time settled into its current rhythm. Others proposed it might be a refugee from a previous cosmic cycle, a survivor of an earlier iteration of the universe before the Big Bang, the wildest hypothesis. That dark energy which accelerates the universe's expansion hasn't always behaved as we think, meaning our estimate of cosmic age could be catastrophically wrong. Yet the most compelling clue might lie closer to home. Recent studies suggest the star's extreme age could be an illusion caused by an unseen companion, a dim white dwarf whose gravitational influence siphoned away Methuselah's outer layers long ago, leaving behind a deceptively primitive core. If true, the star isn't older than the universe. It's just been stripped down to its earliest form, like an ancient tree reduced to a single growth ring. For now, HD 140283 remains an enigma coiled at the heart of its six-star family, a celestial paradox that whispers uncomfortable truths about how little we truly understand time's first chapters. Every photon from its shimmering surface carries a question. Are we misreading the cosmos's birth certificate, or is there something far stranger lurking in the darkness between the stars? Cygnus X1 has always been a rebel, a black hole that refuses to play by the rules. But what if its most infamous anomaly, those bizarre gamma-ray flares that flicker like a malfunctioning strobe light, isn't just random chaos? Some theorists are daring to ask a question straight out of science fiction. Could this sextuple system's black hole be hiding something far stranger than a singularity? Something like a wormhole. The idea isn't as far-fetched as it sounds. Einstein's equations once hinted that wormholes, hypothetical tunnels through space-time, could exist, but only under conditions so extreme they seemed impossible. Enter Cygnus X1. Unlike typical black holes which devour matter in predictable patterns, this one spits out gamma-ray bursts with eerie regularity, as if something on the other side is tugging at the fabric of reality. The flares don't match accretion disk models or standard jet theories. Instead, they pulse with a rhythm that mirrors theoretical projections of a traversable wormhole's throat, a tunnel held open by exotic matter or negative energy. Here's where it gets wild. Recent simulations show that if a wormhole existed here, its gravitational lensing effects could perfectly explain the system's odd stellar motions. The black hole's 5 companion stars don't just orbit, they wobble, their paths subtly warped as if space itself were folding around an invisible structure. Even more compelling, the gamma flares align with these gravitational hiccups, flaring brightest when calculations suggest the wormhole's mouth might briefly stabilize. It's like the system is giving us coded directions to a door we can't yet see. But the real smoking gun might lie in the radiation itself. Wormholes, in theory, should emit unique high-energy signatures as particles traverse their boundaries. Cygnus X1's flares match these predictions too closely to ignore specific energy, spikes that resemble matter being scrambled and reassembled as it passes through. One particularly bizarre outburst in 2019 even showed particles accelerating faster than the local speed of light, a telltale sign of spacetime itself being manipulated. Of course, skeptics pounce on alternative explanations. Maybe the flares stem from colliding magnetospheres or a hidden neutron star caught in the black hole's grip. But none of these theories account for the full suite of anomalies: the timing, the particle energies, the gravitational wrinkles. A wormhole, improbable as it seems, neatly ties them all together. If true, the implications are staggering. Cygnus X1 wouldn't just be a black hole, it'd be a cosmic subway, a shortcut through the universe whose other end might open anywhere. Or anyone. Suddenly, those gamma flares aren't just outbursts, they're echoes from the other side, hints of a connection to a place or an era we can't yet fathom. And if nature built one wormhole here in the chaos of a sextuple system, who's to say others aren't hiding in plain sight? The universe, it seems, keeps its most audacious secrets tucked inside its most violent neighborhoods. From vampire stars stealing cosmic lifeblood to gravitational ghost towns hiding dark matter, these 30 bizarre sextuple systems have rewritten the rules of stellar physics right before our eyes. We've witnessed stars swinging through space like cosmic pendulums, diamond factories forging entire worlds, and even potential wormholes flickering in the heart of black hole systems. Each discovery peels back another layer of the universe's complexity: systems where time flows differently, where dead stars refuse to stay dead, and where planets somehow cling to existence against all gravitational odds. What makes these celestial oddities so revolutionary? They prove that gravity's dance isn't limited to simple pairs or trios. Nature builds intricate stellar families where 6 suns interact in symphonies of chaos and precision. Where astrophysics textbooks once declared certain configurations impossible, real-world observations now show stars cooperating in ways that defy our models. These systems aren't just scientific curiosities, they're cosmic laboratories demonstrating how matter behaves under conditions we can't recreate on Earth: extreme magnetism, warped space-time, and particle acceleration on scales that dwarf our greatest machines. The implications ripple across astronomy. If planets can form in these gravitational war zones, how many more exotic worlds might be hiding in similar systems? When stellar mergers create chemical anomalies like HV 2112 impossible elements, what does that mean for the building blocks of life across the galaxy? And if dark energy really can influence small star clusters as we saw in one SWASP J093010, does that hint at a fundamental flaw in our cosmic expansion theories? Every answer unlocks 10 new questions. Now it's your turn to weigh in which of these 30 discoveries left you rethinking everything you knew about stars. Was it the diamond-forging powerhouse HD 144548, the runaway fugitive star of VV Orionis, or perhaps SS-433 antimatter jets that could power civilizations? Drop your thoughts in the comments below, and if you're hungry for more cosmic mysteries, hit subscribe to join us as we keep unraveling the universe's greatest puzzles, one mind-bending system at a time.